All right, so in this lesson, we're going to talk about air resistance. Now, in order to learn about air resistance, we first need to talk about drag force. Drag force is a resistive force that acts on an object that is moving in a fluid. So this would be a solid moving in, say, a liquid or a gas. And the drag force will act opposite to the motion of the object because it's a resistive force. Now in this lesson, we're going to specifically talk about a ball that is dropped in the presence of air. So the object in this case will be a ball, and the air is going to be the gas upon which it is moving through. Our goal is to find the velocity as a function of time of a ball that is dropped in the presence of air. Okay, now to get started with this, we're going to start by drawing a free body diagram on this ball as it falls in the presence of air. Now, as this ball falls, it will have two main forces acting on it. One is the weight down, and the other is the drag force upward, and we're going to call that our drag force, or the resistive force because of the air. Now in this example, the ball will be falling downward, so we're going to have a velocity downward. There will also be an acceleration downward, and therefore I'm going to make downward positive in this problem. So I'm assigning direction and making downward positive. Now we're going to make an assumption that as this object falls downward through the air, that the air resistance that it experiences is laminar, or there's a laminar flow. So when we make that assumption, then we can go ahead and assign the equation for air resistance of being negative kV, where K is a constant and V is the velocity of the ball. So as the velocity of the ball changes, so does the drag force due to the air. Now I'm going to go ahead and apply Newton's second law to this ball as it is falling downward. And I'm going to add up the forces acting on the ball in the vertical direction and set it equal to MA. Now there are two forces acting on the ball. One is the weight, which is acting downward and is therefore positive. And the other is the drag force, which is acting upward. So I'm going to give that one a negative value because I assigned downward as positive, and that's going to be equal to MA. I'm going to go ahead and plug in my equation for my resistive force into my Newton's second law equation, and notice that I'm not bringing the negative over with that, and that's because the negative, which I will circle in green here, tells us that when we draw our free body diagram, the drag force is going to be in the opposite direction to motion. Well, I already drew that in my diagram, so when I write out my equation for Newton's second law of motion, I can now look at my diagram when I add up the forces and determine whether a value should be positive or negative. So plugging in the kV, it will look like this. Now the next thing we need to realize is that if we want to find velocity as a function of time, we need to rewrite the equation as a differential equation. And to do that, what I'm going to do is rewrite my acceleration variable as dv over dt. Now, before I solve for velocity as a function of time, I want to go ahead and take this moment to discuss terminal velocity. So terminal velocity is when your drag force value upward equals the weight downward, and the object therefore is no longer accelerating because the forces are balanced, and the object is going as fast as it's going to go. That is called terminal velocity. So I want to take a moment using the equation that we just came up with and plug in 0 for acceleration and solve for velocity. This will give us terminal velocity. Okay, so rewriting or writing the equation above again. And for acceleration, I'm going to plug in 0. Then what I'm going to do is add kV to both sides. And I end up having the weight is equal to kV. Then what I'm going to do is divide both sides by the constant k. And I now have an expression for V. Sometimes people will write a little subscript of T there for terminal, and that will be equal to mg over k. So this would be our terminal velocity value. Okay, so now let's find the velocity as a function of time. So we are going to start with our equation from above, our differential equation, where we have dv over dt for acceleration. Now, first thing we're going to do is do separation of the variables by, in essence, putting dt on both sides. Then we have something that looks like this. Then I'm going to divide both sides by the quantity mg minus kv. And I'm also going to divide both sides by m. So these m's cancel and this quantity cancels on this side. So I'm left with 1 over m dt is equal to 1 over the quantity mg minus kv dv. So the next thing I'm going to do is integrate. And for my integrands, I'll have initial time to final time, initial velocity to final velocity. Now, when I integrate 1, I'm basically going to have t, and I'm going to evaluate my final time and my initial time. That's the left side. On the right side, it actually ends up being the natural log of the absolute value of mg minus kv. Of course, this is the antiderivative, so I also need to divide by negative k. That means if I took this value and took the derivative of it, I would get what was in the original integral, which is 1 over the quantity mg minus kv. And then we will evaluate at final velocity and initial velocity. At this point, I am going to multiply negative k on both sides. See if I could fit that in there so that it cancels right there. And then I'm left with negative k over m. And if I evaluate, I'll have t minus t sub naught. Of course, that's on the left side of the equation. And then on the right side of the equation, I'm going to have a natural log of mg minus kv minus the natural log of mg minus, running out of room here, kv sub naught. Let me rewrite that for you on the next page. So let's do it on the next page here. Give ourselves a little more room. So it's going to be a negative k over m times the quantity t minus t sub naught is equal to the natural log of mg minus kv minus the natural log of mg minus kv sub naught. There, that's a lot better. Now, if we make the assumption that t sub naught, the initial time, starts at 0 seconds, and my initial speed starts at 0 meters per second, then I plug in zeros for those values, and I'm actually left with negative kt over m is equal to the natural log of mg minus kv minus the natural log of mg. This is the same thing as writing this way. Now what we're going to do is use Euler's number. That's our trick here to get rid of the natural log. And what I end up getting is this. Which of course is just this. Now eventually I want to solve for velocity. That will give me the velocity as a function of time. So I think the next step I'm going to do here is multiply each term by a -1. And when I do that, I get this. And then I'm going to go ahead and add 1 to both sides. And when I do that, I get this. My last step is I'm going to multiply both sides by mg over k. And in doing so, I get some cancellations where I actually just have an expression for v. So let me rewrite that for you. And that, folks, is a velocity as a function of time while the ball is falling in the presence of air. Now, how would we then represent the acceleration as a function of time? Okay, so finding the acceleration as a function of time, we just want to remember that your acceleration of a function of time is the derivative of your velocity as a function of time. So looking at the above equation, we want to use that above equation to do that. And actually, I'm going to go back by looking at that equation and rewriting it by distributing our mg over k. So I'm going to have mg over k minus mg over k times Euler's number to the negative kt over m. Now, the derivative of this with respect to time then is just going to be the negative mg over k times Euler's number. And then according to the chain rule, I then need to take the derivative of the exponent because that's where the time variable is. And so we're going to multiply that by the variable of that exponent, which is going to be negative k over m. And we're actually going to bring that negative k over m to the front of this equation so that it will look like negative k over m times a negative mg over k multiplied by Euler's number to the negative kt over m. Now what ends up happening is these m's cancel, the k's cancel, the negatives cancel, and I'm left with an acceleration as a function of time is equal to the acceleration due to gravity g times Euler's number, negative kt over m. This could also be written like this: acceleration due to gravity over Euler's number, kt over m. So there is an expression, or an equation rather, for the acceleration as a function of time. So what about graphing? Let's do a graph of velocity as a function of time, this motion, and then a graph of the acceleration as a function of time for this motion. Okay, now for a velocity as a function of time equation, if we were to graph the velocity as a function of time, we can use our velocity as a function of time equation to determine what happens as time goes on. So hopefully you can see in this equation here that as time goes on, we basically in effect have Euler's number to infinity. And so this term right here, as time goes on, basically approaches zero. So as time goes on, your velocity as a function of time approaches mg over k. And that, if you recall, is also the equation for terminal velocity. So this basically is the terminal velocity value. The velocity starts at 0 if the ball is dropped, and then it approaches, we have an asymptotic relationship here, and the velocity approaches the terminal velocity as time goes on. Now I know that the curve looks like this because if I pick little points along this curve and draw tangents to those points, I can see, and by the way, these tangent values just represent the acceleration. I can see as time goes on, the acceleration is approaching a zero value as well. And this, of course, is what happens when an object reaches terminal velocity, is that the acceleration approaches zero as well. Okay, so what would the acceleration versus time graph look like? All right, well, using the acceleration as a function of time equation, hopefully you can see that as time goes up, we are going to have our number in the denominator approaching infinity. And as a number in a denominator approaches infinity, then our answer, and in this case acceleration as a function of time, approaches zero. So, and let's also look and see what happens when t is 0. So again, when we look at this equation here, we can see that when t is equal to 0, the acceleration is actually equal to the acceleration due to gravity. And as t increases, then a approaches 0. So we can see that at a time of 0, my acceleration is indeed the acceleration due to gravity. And just so you know, when we look at these values, we're just looking at the magnitudes of these values. So that's important to point out. Now, as time goes on, the acceleration is going to approach 0, and it's going to have another asymptotic relationship that looks something like this, where the function is approaching the t-axis as time goes on. Now, I know that the curve looks like this because I know the area between the curve and the t-axis is going to give me the change in velocity. So I want to show you two different changes in velocities. One we'll call blue, and the other one we'll call green, and with about the same amount of time here. And what I want you to see is that the change in velocity in blue is actually less than the change in velocity in the green, which means as time goes on, the object is approaching a terminal velocity, or it's reaching a more stable velocity, and that's what this curve shows us. Well, that's it for today. I hope you enjoyed this lesson on air resistance, and take care.